Hi everyone, Mr. Scott here again. In preparation of finishing up the acids and bases unit, of course it's been a while since you learned it, so here is a quick 2-video refresher. As you can see, this is acids and bases review part 1. This will be a 2-part video series, I guess, that kind of is intended to refresh your memory on acids and bases before moving on to anything else. So let's get into it. What you should have out for right now, let's get this out of the way, is reference table. Flip to page 6. Page 6 has table L, M, and K, I believe. You're going to need it. Those are the tables that are referring to acids and bases. You need pen, pencil, and fresh sheet of paper. If you are new and have not been here in a while, if you see the little icon, this write down icon in the bottom left, that means that I want you to write it down. I'm going to do my very best to try to pause or tell you to pause the video and write down notes at the end of each slide. If I don't, just go back and write it down anyway. So what we're going to do for today, we're going to begin with reviewing the Arrhenius definition of acids and bases. We'll take a quick peek at tables K and L. We'll discuss electrolytic solutions, which I hope you haven't forgotten that I taught you about in solutions. We'll do a little pH review, which we'll do, we'll do pH, strong acid versus weak base versus strong base, and then we'll talk a little bit about neutral too. And then how many times more acidic or basic, and litmus tests. So defining acids, get this out of your way. An Arrhenius acid, it's any substance that produces an H plus or H3O plus as the only positive ion in solution. So that H plus and H3O plus, they're essentially the same thing, and I'll show you that right here. It's important to know, though, that this is your definition of an acid anytime that this H plus is produced. So for the first example, this looks a little bit like the one that you did in class, but you did HCl and I have HBr. Same thing. Doesn't matter. So you can see that H plus is the only positive ion, the H plus right here, that has dissociated from the HBr, which makes HBr an Arrhenius acid. If it occurs in water, this reaction occurs in water, so it would be HBr plus H2O. That is when you would end up with the H3O plus. So you can see that it just has an additional H to water. So water is H2O, H3O plus is your hydronium ion. That's what it's called. It means the same thing as an H plus. H plus, H3O plus, they're synonymous essentially. It just depends on if you include the water or not. If you see either one of these, that's what's showing that a certain substance is an acid. You'll see that the H and HB are dissociated and combined with water to become H3O plus in the second example. So your HBr combined with water, the H got transferred over, and you end up with the hydronium ion and the bromide ion. Again, very important, you must know that H plus equals H3O plus. They both symbolize a substance being an acid. Something like NaCl, table salt. Why isn't it an acid? It's not an acid because this Na plus is the only positive ion in solution. There is no H plus positive ion in solution. So this would be the time. Take a second, pause the video, and write all this down. Defining bases. Very similar to defining your acids, except we're talking about the OH minus presence rather than the H plus presence. So an Arrhenius base is any substance that produces OH minus as the only negative ion in solution. And again, I have an example. Sodium hydroxide. Sodium hydroxide dissociates into Na plus sodium, the sodium ion, and then the hydroxide ion. OH minus is the only negative ion in solution, which makes NaOH an Arrhenius base. If you were to do this with water, it would be the same thing. You would still get the OH minus. Again, we'll talk NaCl, for example, 2. Since Cl minus is the only negative ion in solution, that means that NaCl is not a base because it does not have the OH minus present in solution. This would be the time. Pause the video. Write this down. Okay, common acids and bases. We're talking table K and L for right now. I'm just going to get this out of your way because some information is going to pop up in the bottom right-hand corner. This is available to you for any test that you would have taken. So table K talks about your common acids, while table L talks about your common bases. Of course, based off of the definitions that we just talked about, these all apply. But there are some things that just look a little weird here, so I wanted to clear it up. NH3, here, your aqueous ammonia, which we've talked a little bit about ammonia. Since it's a polar compound, it's one of the most common polar compounds similar to water, so it comes up every so often. NH3 is a common base, but it does not produce OH- by itself. However, it does produce the OH- when combined with water. I don't want you to write this down. I just wanted to talk about it a little bit in the video to show you why this is on the common bases chart. So it is on the common bases chart because NH3 plus H2O becomes the ammonium ion and the hydroxide ion. So again, OH- being the only negative ion in solution, that makes it an Arrhenius base. CO2 itself, you'll see CO2 over here. CO2 itself is not an acid, of course, but CO2 in water makes H2CO3. So you'll see this H2O and then CO2 combination comes up with carbonic acid, H2CO3. So that's why the CO2 is here. There's nothing for you to write down here. Again, I just wanted to discuss it a little bit. Recall your electrolytic solutions. Let me just get this out of the way since it's cut off. I'm covering up solution of non-electrolyte. It just got cut off in the PowerPoint slide. So you'll remember from the acids and bases activity that I was still there for, that both acids and bases can conduct electricity. And we also talked about electrolytic solutions when we did the solutions activity way back when, in the middle of December, in the middle of February, while I was still there. So you'll recall that, and therefore they're electrolytes. That's what we talked about. When a solution can conduct electricity, that makes it an electrolytic solution. But what allows an electrolytic solution to conduct electricity? This is just a little refresher. Of course, it is your mobile ions. This would be the time. Pause the video, and I want you to only write down what is underlined. Focus on that. Only what's underlined. pH scale, the power of hydrogen, as we talked about in class. So, what I want you to write down, and I think it may pop up later, but I want you to write this scale down. If you don't already have it in your notes, write it down again, because it's really important to know this and know where everything stands in relation to itself. So you'll see a bunch of things pop up in the middle of the screen here, and I'll discuss it, but I'm really going to be referring to down here. So at a pH of 7, the H plus ions equal the OH-. So your hydrogen ions equal your hydroxide ions. And that is where a compound is neutral. So at a pH of 7 is your neutral point of a compound. And this is where acidity equals basicity. So it's not acidic or basic, it's neutral. 1 to 2, in this area to the very left of the pH scale, you'll see your strong acids. Whereas just a little off to the right of your strong acids is your weak acids. So in between strong acids and neutral, you'll find your weak acids. Then you see neutral, which we just talked about. And then 8 through 11 is your weak bases, give or take. It depends on the substance that you're talking about, honestly. But it's a good range that at least in between the 8 to 11 mark is typically your weak bases. Whereas your strong bases will be all the way to the right of the pH scale. Basicity may also be called alkalinity. You may see it, probably not anymore, but it's possible that you may see it. Again, it's really important to know that the H plus ions equals an acid and OH- equals a base. Okay, so I do have the write down. So this would be the time, pause the video, write this stuff down, just like I talked about for the last minute or so. pH scale continued. Get this out of your way. The pH scale is logarithmic. It means it's based on the power of 10. Each step on the pH scale is tenfold change, and it changes by a power of 10. We talked about this in class. I very specifically remember talking about it in class. Again, I'm just trying to refresh your memory on all of it. So if distilled water has a pH at exactly 7 and lemons have a pH of 2, how much more acidic are lemons? So if it goes by the power of 10, meaning there's a 10-fold change, how you want to solve these problems is write out all of the steps going from 7 to 2, essentially seeing how much more acidic using the base power of 10. So if you write down your 7 to 2, once you do that, you can then count using powers of 10 in order to see how much more acidic it is. So you would start at the next number. 10 times would be at 6, 100 times at 5, 1,000 times at 4, 10,000 times at 3, and then 100,000 times at 2. So therefore, a lemon is 100,000 times more acidic than distilled water. And that's based off of the fact that your pH scale is logarithmic and it's based on a power of 10. So I have another example here. Get this out of your way. That I want you guys to right now pause the video, read the example, try it on your own, and then start the video back up and I will discuss the answer. Okay, so if you go from 6 to 8, you're trying to find how much more basic baking soda is than milk. So if milk has a pH of 6, slightly acidic, and baking soda has a pH of 8, slightly basic, how much more basic is the baking soda than the milk? You'll see that in writing it out, you go 10 times, going from 6 to 7, and then from 7 to 8, 100 times. So baking soda is 100 times more basic than milk. Go back. If you need to, if you haven't written this down yet, I didn't put my little write down. If you need to write this down, if you feel that it would help you to refresh your memory, you don't have to write it down. It's fine if you don't, but you did examples very similar to this in class, and I wanted to jog your memory on them a little bit. If it'll help you to write them down, please do. Pause the video if you need to, and write anything you need to down. Okay, litmus tests. We talked briefly about this in the activity that you guys did while I was still there. I wasn't teaching, but while I was still there, you discussed that acid turns litmus paper red. So as you can see, this is kind of what a universal litmus paper would look like, and the colors that you would come up with going from acidic to neutral to alkaline. So your red to your blue. Whether you're using red or blue litmus paper, it doesn't matter. If it's red litmus paper, it will stay red in an acidic solution. And if you're using blue litmus paper, as you can see here, the litmus paper will turn red in an acidic solution. So acid converts blue litmus into red. It's important to know that. And you'll see I included the little trick that Miss Miller teaches you guys. She taught me, and it's still stuck with me for all this time. But base turns litmus paper blue. So as you can see, your red litmus paper would become blue. If you were to take and stick the blue litmus paper in a basic solution, it would not change colors. Typically, you'll see red or blue litmus paper, but you may also see a universal pH paper, which is kind of the yellow. It's the one that you guys use to put on your tongue. And so you'll see that using a universal pH paper, if you're dipping it into a basic solution, it'll come up as blue purplish. And that's because, again, your base turns litmus paper blue. So here is the little, I guess, thing Miss Miller uses to remember it is acid ends in D and red ends in D. So that right there is a little reminder of acid and red. Blue starts with B and base starts with B. So again, your blue litmus paper means base. If you guys have any questions, this is just part 1 of the acids and bases review. In the next video, I'm going to get into neutralization reactions and indicators. So this was kind of the first part. I know I went quickly through things. If you have any questions, at all on anything that was covered, if anything's not clear, you know where to find me. Through Remind, through email. I hope this finds you guys happy, safe, healthy in all of this isolation. Miss you guys a ton. And I look forward to hearing from all of you soon. So have a good one, guys.